Ladies and gentlemen, you are welcome. I'm Fayssal Amran. I'm from Farhat Abbas City Fund University. I have the honor to participate in the European Power Electronics Conference 2020 with the paper 71, Hardware Implementation Study of Variable Speed Wind-TurbineDFIG Generator in standalone mode. So in order to understand more deeply this research work, so we'll start with parts of our poster. We have 5 parts. I'm trying to explain it one by one in the future slide, and we will finish, of course, with the conclusion and some perspective. So we'll start with the first part of this poster. In the left side we have the wind system picture, which is based on 3 aspects: aerodynamic, mechanical and electrical aspects. So the first choice is DFIG generator. So we choose this generator because the rotor needs only 30% from the rated power, and we have also the mode of the generator, which depend basically on the wind system wind speed variation. We have a sub and super synchronous mode. So in order to apply these different modes, we have to modulate and design the power control of our system. And we will make some experimental simulation validation. So here we have the part number 2 of this poster. In the left side we can show the picture of the proposed DPC algorithm, which based on the EPE controllers. We control the rotor direct and transversal currents, which are basically the image of the active and deactive power. We can generate switch signals which control the AGBTs of the inverter. We use the LCL filter between the rotor and the inverter, and I'm trying to explain why this choice in the future slide. So we will justify our choice. And we have the starter is connected directly into the error load with a capacitive bank. So for this reason we can say that we have the standalone mode. In the part number 3 of this poster, we make a comparative study between L and LCL filter. We can show a very big improvement using the second proposed filter, the LCL filter, especially in the rotor and stator waveforms. We can show that these waveforms are perfectly sinusoidal. So we can say that the power quality is improved in this case, and we will keep this type of filter in the future experimental tests. So in the part number 4 of this poster, we can show the closed loop of the transfer of the wind system transfer function. We defined the Ki and the Kp, and we will make a comparative simulation study between the proposed and classical one. We can say that the wind system of the proposed control is improved compared to the classical one, especially in the response time, power tracking, overshoot, and power error. We can show the simulation results. In the bottom side we have the zoom. So here in part number 5 in this poster, we apply an experimental test, speed variation and rotor current variation. So using this experimental test, we can show the different zone: stable zone, sub and super synchronous zone. So depending on the wind speed variation, we have the rotor power flow. So the rotor can absorb or inject the power depending on the wind speed variation. For example, the rotor can absorb the power in the case when the wind speed is below than 1500 RPM, revolution per minute. We can show that in the bottom side the rotor current variation using trapezoid and step forms, and we can show that the high performances wind power are noted, especially in transit and steady states. So as conclusions, high wind power control performances are proposed in this research work. So we have a hardware implementation simplicity is advantage, and the Ki and the Kp again depend basically on the wind system parameters, so this is a drawback. And as perspective, we have grid connection topologies. Finally, I want to say thank you for your attention and passion. Thank you.